Morning. Today I want to talk a little bit about free fall. So we were talking about the ramp yesterday, and one of the things about the ramp is that the acceleration of the object on the ramp is actually determined by the steepness of the ramp. Let me show you what I mean. So if you look at a ramp like that's this, and you put a ball on the ramp, the ball's not going to accelerate at all. It's just going to sit there. If you make the ramp a little steeper, it's going to accelerate down the ramp. If you make the ramp even steeper...
Good morning, Grosse Pointe North staff. The senior class would like to invite you down to breakfast in the student union. Thank you.
It'll have even a larger acceleration. And so how do we orient the ramp so that we have the largest acceleration possible? Well, what if we put the ramp so that it's oriented vertically? What we'll notice is that the ball is just going to fall straight down. And this is obviously the maximum acceleration that you could get. So when we measure this, okay, when we measure the acceleration of this ball, we find out that the acceleration is equal to 10 meters per second per second. Now, what does that mean? For us, that means that for every second that the ball is in the air, the speed is going to change by 10 meters per second. But the thing about acceleration is that it doesn't care the direction of your velocity at all. The acceleration is going to be the same regardless. So, because the acceleration is in the down direction, we call this the acceleration due to gravity, or we call it the free fall acceleration. And to represent this, we use the little baby g. Negative 10 meters per second per second. So in this case, what it means is that regardless of the direction of your velocity will change by negative 10 meters per second, or for every second, or it'll change 10 meters per second in the down direction for every second. So let's look at a couple scenarios. In one scenario, you just drop a ball. So this dot picture represents the ball as it falls, and we see it at 0, 1, 2, 3 seconds. If we do that, we can get a sense of the velocities. So if you just take a ball and you just drop it, the initial velocity is 0. So then what's the velocity at 1 second? Well, for every additional second that it falls, the velocity changes by negative 10 meters per second. Another second of time goes by, the velocity changes by another 10 meters per second, so now it's... Another second goes by, it changes by another. So this gives us a sense of how an object falls. It's in free fall, which means, and free fall is kind of a colloquial term that we use, which means there's no other forces on it except the earth pulling it down. So as it's falling, it gets faster and faster and faster, all right? And the velocity changes by negative 10 meters per second for every second that it falls. In another scenario, what if you were to throw the ball upward instead? In this case, if you were to throw the ball upward, what would happen to its speed on the way up? We can see from this scenario that as the ball's on the way up, it slows, and then on the way down, it speeds up as it goes. Can we figure out what the velocities are at in this scenario? What I like about this is there's a clue here. If I take this marker and I throw it up and it comes back down, the velocity was positive on the way up and negative on the way down. What had to happen at the very top? Well, if it was positive before and negative after at the very top, it had to have been 0. And if you watch it, you can see that you can see that it had to stop for an instant. So that means that up here, the velocity is 0. So what did the velocity have to be just before, and what is the velocity just after? Well, if it was 0 and then it starts to fall, we know it had to be negative 10. Negative 20. Negative 30, because for every second it's falling, it changes by negative 10. But here's the cool part. If we apply symmetry principles, because you know symmetry is your friend, what had to have been the speed before? And the initial speed? So if you throw the ball up at 20 meters per second, 1 second later, it's going to be negative 10, because according to the acceleration, the velocity changes by negative 10 meters per second for every second that it is in the air. That's why free fall is a hard word, because it's not actually, like falling, we think falling is velocity down, but you can fall with velocity up. It just means that the only thing pulling on you is the earth. So the initial velocity was 20 meters per second. Subtract 10 gives you 10, subtract 10 gives you 0, subtract 10, negative 20, negative 30. So this is our free fall acceleration concept. One of the things we want to know, if we go back to our original scenario, is how far does the ball fall in just 1 second? Well, to understand that, we're actually going to employ the area under the curve scenario. So what we'll notice here is that at time 0, the velocity is 0. At 1 second, the velocity is negative 10, negative 20, negative 30. If I graph that over here, 0 time, the velocity is 0. At 1 second, the velocity is negative 10, 2 seconds, negative 20, 3 seconds, negative 30. And what I like about this is very easy to understand. The velocity changes linearly. If I look at the slope of this is the acceleration, and the slope of this line is clearly negative 10. If you change negative 30 in 3 seconds, the slope is negative 10. Can we use this to find out how far it falls each second? Well, we totally can, and it's easy because if I shade the area between your line and the horizontal axis, and this is one of the cases where, you know, the term area under the curve doesn't really help because it's not a curve and the area is not actually under. If I shade the area under, like I could shade down to infinity, so it's the area between your line and the horizontal axis. And when I look at this, what do I notice about this area? Well, this shape is a triangle. How do you find the area of a triangle? Area of a triangle is 1/2 the base times the height. The base is 1, the height is 10. So 1/2 of 1 times -10 is -5, which means that the change here is -5, and that means over here that the ball fell 5 meters in the first second. What about after 2 seconds? After 2 seconds, we can use the same thing. We're going to do the full 2 seconds. So between 0 and 2 seconds, 1/2 the base times the height. The base is 2, the height is -20. 2 times -20 is -40, and half of that gives you -20, which means in the first 2 seconds, it fell a total of 20 meters. What about after all 3 seconds? After all 3 seconds, 1/2 the base times the height. The base is 3, the height is -30, which means it fell a total of, or the change is -45, so the total distance it fell here is 45 meters. This gives us a sense of how an object falls. Now, this is the hard part. If I had said, how far did the object fall in the first second, I think our instinct is to say, oh, well, it fell 10 meters, because you see this 10 and you see the meters, but consider this as a problem. The initial velocity is 0. The final velocity in that 0 to 1 second time interval, the final velocity is 10. It started at 0. So the average velocity in this second is only 5 meters per second, and it lasted for 1 second, so we got 5 meters. It couldn't have gone 10 meters in the first second because it doesn't reach 10 meters per second until the end of that first second. Now, what does this mean for us? Well, just like the ramp problem, the acceleration is constant. And so, our acceleration, we're going to use baby g for the free fall acceleration, it's -10 meters per second per second. And so our equations that's one of our constant acceleration equations. That's our other constant acceleration equation. These, we're going to change a little bit because now all of a sudden, right, we're now moving in the y direction, we're now moving in the up and down direction. And so instead of delta x,